Ever been walking in the rain and noticed how it seems to be slanting towards you, even if you know it's falling straight down?
Mm.
Or how about that wind you feel hitting your face when you're cycling on a completely still day?
Yeah, that's a good one too.
Okay, let's unpack this. Because those everyday experiences, simple as they seem, they give us a little glimpse into something pretty mind-blowing. How our own motion through space affects how we see the stars.
It's true. And this seemingly simple effect has really profound implications. It
Yeah.
leads us right to the heart of our discussion today, stellar aberration,
Solar aberration, right.
which is the apparent shift in the positions of stars caused simply by our velocity as observers. It's not just some minor detail. It's really fundamental to astronomy.
And it's shaped our understanding for centuries, right?
Hmm.
And it's still crucial today for these incredibly precise measurements astronomers are making.
Absolutely. Still absolutely essential.
Exactly. And for you listening, whether this is maybe a brand new idea or perhaps something you're looking to understand a bit more deeply, our goal today is to really get to grips with what stellar aberration is,
Hmm.
why it matters, and how it's actually led to some incredible discoveries about our place in the galaxy. We've got some truly fascinating material that brings this all to life.
Yeah, and maybe to connect this to the bigger picture, we'll start with the basic concept, how Earth's movement around the sun creates this apparent shift. That's sort of the first layer.
Okay.
Then we'll journey out to the galactic scale, explore the more subtle and actually more recently detected effects of the sun's own movement around the Milky Way.
So going from our local neighborhood right out to the whole galaxy. Cool.
That's the plan. From our orbit to the galactic carousel, so to speak.
So let's dive into the basics then. Think back to that rain analogy.
Right.
If you're standing still, it looks like it's coming straight down. But the moment you start moving forward,
It seems to angle towards you.
yeah, it's like your motion is adding vectorially to the rain's downward motion.
Precisely. That's the core idea of stellar aberration, this combination, this vectorial addition of velocities. So instead of raindrops, imagine starlight.
Light from a distant star racing towards us.
Yeah. And instead of you walking, picture the Earth speeding along in its orbit around the sun.
Right. And Earth moves fast, about 30 kilometers per second in its yearly trip. That's incredibly quick.
It really is.
So because of that motion, the apparent position of a star in the sky shifts just a tiny bit in
Yeah.
the direction Earth is currently moving.
Exactly. And the scale of this shift, well, it's remarkable when you compare Earth's speed to the speed of light.
Which is just staggering, 300,000 kilometers per second.
Roughly, yes. So Earth's speed is much smaller, obviously, but it's still enough to cause a measurable angular displacement. That ratio, our speed v over the speed of light c,
V over C.
it works out to about 0.0001 radians, which translates to roughly 20 arc seconds on the
That's
sky.
20 arc seconds.
Yeah.
Okay, that sounds tiny.
Ah. Well, in everyday terms, yes, it's minuscule. But in precision astronomy, 20 arc seconds is actually quite significant. It's definitely measurable.
Okay.
Think about trying to see like a small coin from maybe a kilometer away. That's the sort of angle we're discussing.
Gotcha. And here's where it gets really interesting, I think. This 20 arc second shift isn't constant, is it?
No, exactly, because Earth goes around the sun. So 6 months later,
We're on the opposite side of the orbit, moving the other way.
precisely, moving in the opposite direction. So that apparent 20 arc second shift completely reverses.
So it wobbles back and forth.
It does. This back and forth movement over the course of a year is what astronomers call annual aberration. It's the wobble in the apparent positions of stars caused by our yearly trip around the sun.
Annual aberration.
Okay.
And it's probably worth noting quickly, there's also a smaller effect, diurnal aberration.
Diurnal, so daily.
Yes, caused by Earth's rotation on its axis. It happens over just 24 hours, and the effect is smaller, but it's still there. Another layer of our motion influencing what we see. Fascinating. Okay, so we have aberration, this apparent movement due to our velocity. But the sources also make a really clear distinction between this and another key concept, parallax. Can you help us untangle those?
Absolutely. Good question, because they often get mentioned together, especially historically. So both aberration and parallax cause apparent shifts in star positions, yes, but the causes are different.
Okay.
Aberration, like we said, comes from the observer's velocity, how fast we're moving. Parallax, on the other hand, comes from the observer's changing position. where we are.
Changing position,
Exactly.
like looking from different spots.
Exactly like that. Hold your thumb out at arm's length, close one eye, then the other.
The thumb jump trick.
Yeah, your thumb
Yeah.
seems to shift against the background, right?
Yeah.
That's parallax. Your different viewpoints, your two eyes create that apparent movement. In astronomy, the viewpoints are Earth's position at different points in its orbit.
Right. So parallax is about seeing a star from two different places, 6 months apart usually, and using that to measure its distance through triangulation. Whereas aberration happens because we're moving, even at a single point in time, as long as we have velocity relative to the incoming light.
You've got it. Velocity versus position. And what's fascinating is how tangled these two ideas became in the history of astronomy.
How so?
Well, for centuries, astronomers were desperately trying to measure stellar parallax. They knew that if Copernicus was right, if Earth really orbited the sun.
The nearby stars should seem to shift against the background stars as we move.
Exactly. That was seen as the smoking gun evidence needed to prove the Copernican heliocentric view. But it was incredibly hard to measure.
And this brings us to James Bradley,
Yeah.
right? Early 18th century. He was trying to measure parallax.
He was. He set up very careful observations of a specific star, Gamma Draconis, hoping to detect that tiny parallax shift over the year.
But he found something else instead.
He did. He didn't find the parallax shift he expected. Instead, he found this other small, systematic, regular shift in the star's apparent position throughout the year.
Which turned out to be
Aberration. After a lot of meticulous observation and, frankly, brilliant reasoning, he correctly figured out it was due to the aberration of starlight caused by Earth's orbital velocity.
wow. And didn't he also use that to estimate the speed of light?
He did, remarkably. From the size of that angular shift, the 20 arcseconds, combined with an estimate of Earth's orbital speed, he calculated the speed of light. His estimate was around 295,000 kilometers per second.
That's incredibly close to the modern value.
It really is, especially for 1729. So this discovery wasn't just finding some weird wobble. It was independent proof that Earth was moving, long before anyone successfully measured stellar parallax. A huge deal.
Amazing. A failed experiment leads to a massive discovery and a measurement of C. Science at its best.
Absolutely.
Okay, so fast forward to today. Our understanding of aberration must be incredibly sophisticated now, especially with space missions like Hipparcos and, more recently, Gaia.
Oh, completely. The level of precision we work with now is just astounding. Think about Gaia. It's orbiting way out at the L2 Lagrange point, 1.5 million kilometers from Earth.
Right.
Yet its own position is known to better than a kilometer, and its velocity, but then 0.2 meters per second.
Wow, that precise.
That precise. And with that kind of knowledge about the spacecraft's own motion, the effects of stellar aberration, including subtle relativistic effects, can be predicted with incredible detail. It's all factored into the massive data processing needed to create those amazing Gaia star catalogs.
So aberration isn't just some annoying distortion we have to remove. It's actually a well-understood phenomenon that we can model and account for precisely.
Exactly. It's part of the calculation.
But the story doesn't quite end there, does it? Because the sources then bring up this even more subtle idea. Secular aberration. What's that about?
Right, secular aberration. This comes into play if the observer's velocity isn't just constant, but is actually changing over time. In other words, if the observer is accelerating.
Accelerating.
Yeah.
Okay. How does that change things?
Well, if your velocity is changing, the direction and magnitude of that 20 arcsecond annual aberration shift will also slowly change year after year. But more fundamentally, the acceleration itself causes a separate, continuous drift in the apparent positions of stars over long timescales.
A drift. Like the stars seem to be moving slowly in a particular direction because we are accelerating.
Precisely. If our measurements are sensitive enough, and this happens over detectable timescales, we might observe this pattern of apparent proper motions, all pointing generally in the direction of our acceleration.
And it seems this idea wasn't totally new either. Someone thought of this way back.
Yeah, John Pond, back in the 19th century, apparently considered this possibility. But, at the time, it was thought to be completely unmeasurable. There wasn't a strong reason to think our solar system had a significant detectable acceleration.
But we now know it does, right? On the grand cosmic scale.
We do. Our sun isn't just sitting still, it's orbiting the center of the Milky Way galaxy. One huge lap takes about, 250 million years?
Something like that, yeah. A galactic year.
And even bigger picture, our whole Milky Way galaxy is moving within the local group of galaxies, and the local group is moving relative to the cosmic microwave background radiation, the CMB, that afterglow of the Big Bang.
Okay, so we're definitely accelerating. Orbiting the galaxy means we're constantly changing direction,
Mhm.
which is acceleration. But how on Earth could we detect that specific acceleration? Wouldn't it be swamped by all the actual movements of stars within the galaxy?
That's the crucial problem. If we only had stars within our own galaxy to look at, disentangling our own acceleration from their individual motions, yeah, that would be incredibly difficult, maybe impossible.
So what's the trick?
The trick is Gaia's ability to observe incredibly distant objects outside our galaxy, quasars.
Quasars, those super bright active galactic nuclei incredibly far away.
Exactly. There are hundreds of thousands, maybe millions of them that Gaia can see. And because they are so extraordinarily far away, billions of light years, their own apparent motion across our sky is practically zero over human timescales.
So they're like fixed points, fixed beacons in the ultra-distant universe.
Pretty much. They form an almost perfect inertial reference frame, a stable background against which we can measure our own motion, including our acceleration.
Ah, okay, that makes total sense. It's like having fixed lighthouses on the coast to measure your ship's drift.
A perfect analogy.
The sources mention some early attempts to measure this secular aberration using radio astronomy with VLBI.
Yes, very long baseline interferometry. These were pioneering efforts. The expected effect, this drift caused by our galactic acceleration, is incredibly tiny, maybe 100 microarc seconds per century for well-placed quasars.
Micro arc seconds, that's minuscule.
It is absolutely at the limit of VLBI sensitivity.
Hmm.
But after decades, literally almost 40 years of collecting data from a few dozen radio sources, they did report a detection, an acceleration measured as about 5.83 microarc seconds per year drift.
Wow. Decades of work for such a tiny signal, that's dedication.
It truly is.
But it sounds like the real breakthrough, the clear detection, has come with Gaia. And apparently measuring this was actually a goal for Gaia from way back.
That's right. A researcher named Bastian pointed out its importance for Gaia back in 1995. And then Kleiner and colleagues, using Gaia's early data release 3,
DDR3, yeah.
they specifically went looking for this effect. They analyzed the measured proper motions, the tiny apparent movements across the sky of over 1.6 million quasar-like sources in the Gaia data.
1.6 million. And what did they find? Did they see the drift?
They did. They successfully detected a systematic pattern in the quasar proper motions consistent with an acceleration towards the galactic center. The value they found was 5.05 plus or minus 0.35 microarc seconds per year.
5.05 microarc seconds per year. Okay, how small is that really?
Uh,
It's almost unbelievably small. It's thousands of times smaller than the typical apparent motions we see for stars within the galaxy due to its rotation. But let me put it in maybe more relatable units.
Please.
That angular drift corresponds to an acceleration of about 7.3 kilometers per second per million years. Okay, still hard to grasp. Any other way?
How about this? It's about 2.3 times 10 to the minus 10 meters per second squared.
2.3 times 10 to the minus 10 meters per second squared. Compared to gravity on Earth, which is nearly 10 meters per second squared.
Yeah, it's about 40 billion times smaller than the acceleration of gravity you feel right now.
Good grief. That Gaia can measure that.
Yeah.
It's just staggering. So, this is the first optical detection of our solar system's acceleration as it orbits the Milky Way.
That's right. First time seen clearly in optical light across the whole sky, using these quasars as the reference frame. And crucially, the sources highlight that this measured value agrees really well with theoretical models of galactic dynamics, how we expect the galaxy, including its dark matter, to make us accelerate.
It's like we're feeling the gravitational pull of the entire galaxy, including the stuff we can't even see, by watching how the most distant things in the universe appear to drift.
That's a great way to put it, using the edge of the universe to probe our local galactic environment.
Right.
And the potential for future Gaia data releases is even more exciting, refining this measurement, making it even more precise.
And what was that other thing you mentioned? Secular extragalactic parallax.
Ah, yes. That's another incredibly subtle effect. It's the apparent shift in the positions of very distant objects, not due to Earth's orbit, but due to the entire solar system's motion relative to the cosmic microwave background radiation itself.
So our motion relative to the leftover heat from the Big Bang.
Exactly. An even bigger baseline motion. Detecting that would be another major achievement, perhaps possible with future Gaia data or next-generation instruments.
Just incredible. Okay, so let's try and recap this journey. We started with, like, rain hitting you when you walk,
The simple analogy, yeah.
and ended up measuring the acceleration of our entire solar system as it orbits the galaxy by watching micro-arcsecond drifts in quasars billions of light years away.
That pretty much covers it. And we've carefully distinguished annual aberration, the yearly wobble, from Earth's orbit.
From this much, much tinier, slower secular aberration, the drift caused by the sun's acceleration around the galaxy.
Exactly. Two distinct effects, both rooted in the principle that our motion affects how we see the universe.
And I think the big takeaway, the aha moment for me, is just the staggering precision of modern astronomy.
Mm.
To detect these cosmic movements by measuring angles that are just almost impossibly small. It really drives home that the fixed stars aren't fixed at all from our perspective. Their apparent positions are constantly being nudged by our own cosmic dance.
Well said. Our view is intrinsically tied to our motion.
So maybe something for our listeners to ponder. If every single observation we make is influenced by our own movement, how might that subtly shape our understanding of other cosmic puzzles? Like the large-scale structure of the universe, or maybe even the nature of dark matter or dark energy.
That's a deep question. It forces us to constantly refine our models and account for our own perspective.
Or maybe think about it this way. If we can now detect our acceleration around the galaxy using quasars, what other, even more subtle accelerations might be imprinted on the light reaching us? Tiny signals waiting for even better instruments to uncover them.
It definitely opens up fascinating possibilities. It underscores that the universe is dynamic and our understanding is always evolving. We really encourage listeners, if this sparked your interest, to dig deeper.
Yeah, look into the Gaia mission itself. It's incredible. Or read about the cosmic microwave background or the whole history of trying to measure parallax and aberration.
Understanding these effects, even the subtle ones, genuinely unlocks a richer, more dynamic, and frankly more awe-inspiring view of the cosmos.